All right, you have been graphing exponential functions, and so you know what the graphs look like and how they move based on what your values are for A and B. So we're going to start looking at now exponential growth and exponential decay of an initial amount. And so we're going to start with this first key concept, exponential growth. Let's look at the definition. If you notice in the definition, you should recognize your exponential function form, y equals a times b to the power of x. Now a has to be larger than 0, so we're going to get into your restrictions here for exponential growth. A is going to be larger than 0 and b is going to be larger than 1. So you're not going to have any of those 1/2, 3/4 like you had in the previous lesson. Now, the base, b, is called your growth factor, okay? So if you're given some easy question that asks what is the growth factor of this exponential function, you're going to look at what the value of b is, okay? Now, what's very important here is that the growth factor is 1 plus, okay? So if you're writing this down, this might be something that you want to highlight, underline so you remember. The growth factor is 1 plus the percent rate of change. Now, we've talked about the percents, that when we use those within equations and that sort of thing, we have to have them written as a decimal. And one way you can think of this is think about your bill. If you're paying your tab at a restaurant, you're going to have to pay the full amount, okay? That would be a 1 in percent form. That would be 100%. So you pay 100% of your bill, plus you're going to add on a certain percent for a tip. So your actual payment at that restaurant is going to be more, so it's growing, than what it initially was because you're paying a tip. You could also think of it in terms of paying taxes as well. But that's why we add that percent rate. We've got the 100% of what we have plus whatever we're going to be growing by, okay, that percent rate of change, and now it's going to be a decimal, okay? So, for instance, if you had 50%, that would be 0.5, and that would be quite a lot if you were leaving that sort of tip. So it would be 1 plus 0.5, which would be 1.5. So you add on your percent rate of change. Now, I'm looking at the algebra part and the graph here together. They've broken down from the definition what each part here represents. Okay, A is your initial amount, and we've talked about that in the previous lesson. So when x is 0, A is your initial amount. B is your growth factor. Okay, it's going to be greater than 1 because remember we're adding in that percent, okay, written as a decimal. And then obviously x is your exponent. So here is what all that looks like together, and then this would be an example of your graph. It's growing. It's a growth factor, so it's going to be increasing. Okay, so you can kind of guess what your decay is going to look like. So let's move on to exponential decay. Here's our definition. Same exponential function form, but this time A is greater than 0, but B is going to be between 0 and 1. Now notice there's not a little equal sign under these inequality symbols. So we're not including the 0 and the 1. We are just simply using all of the numbers that you would find between 0 and 1, like the 1/2 and the 3/4, like what you saw in the previous lesson. So for this one, if someone asks you what is the decay factor for this exponential function, again, you would go to the B. Okay, B is going to be your decay factor. But this time, you've got 1 minus the percent rate of change as a decimal. So this is the reason why it's going to be less than 1. B is less than 1. Because if you take 1 and subtract something from it, obviously the answer that you get is less than 1. Now, you're not going to have 100% of something minus 100%. That would put you at 0. And we will not ever reach 0. There's not an equal to there. We can never reach 0. But you would have that possibly in real life if you were getting something for free. 100% of the bill minus 100% because it's free. But Just think in terms of going shopping somewhere. You have 100% of whatever the shirt might cost, and then you subtract minus whatever that percent rate of change is, that how much you're getting off. Maybe it's a 25% discount, so you take 25% off. So you could kind of think of decay as that, because it is going down. You're not paying as much for that shirt. Now, things that we're dealing with are not going to be shirts and tips and that sort of thing, but just to give you a general idea of what growth and decay are. So your decay factor, again, is your B, and it's going to be between 0 and 1, because you take that 100%, that 1, and subtract out your percent as it's expressed as a decimal. So if we look at our algebra and graph here together, again, they have highlighted here and shown you what each one of these parts mean in your exponential function. Your initial amount, again, is A. B is your decay factor. Remember, decay factor has to be between 0 and 1. And obviously, X is your exponent. And so here's an example of a graph of decay. Notice that we started up pretty high here, and obviously it continues on up, and then we slowly decay. Now, keep in mind, we never reach 0, okay, because we're never going to reach that X axis. We'll never have that x-intercept. All right, so let's take what we know about growth and decay now and apply that to a few examples. In this example, since 2005, the amount of money spent at restaurants in the United States has increased by 7%. Okay, so since 2005, every year the amount of money spent at the restaurants is going up. So that means more people are visiting the restaurant than used to, and it's going up by about 7% each year. In 2005, about $360 billion was spent at restaurants. So that's a lot, and it's only going up from there. It's increasing. Now, what we're going to do is it wants to know if the trend continues, about how much will be spent at restaurants in 2015. All right, well, we can use exponential growth to actually determine that. Now, 2015 is not very far off from here. That's next year. So we can kind of see how this will compare to what we'll see next year. All right, so I'm going to go ahead and bring this up, and let's focus on a little bit at a time. So please don't jump into all this. Let's focus one thing at a time. Think about this. When can you use exponential growth function? Okay, you can use a growth function when the initial amount increases by a fixed percent. Okay. So if it says that in 2005 it went up by 6%, and then 2006 it went up by 4%, and then 2007 it went up by 10%, that's not a fixed amount. So you can't use your exponential growth. In this problem we can, because the fixed percent is 7. We're going up by 7% every year, about 7%. So that's what we're going to use. All right, so relate. Write out the model. Write out the function form here. That way you can see all the pieces you need. And then always define, you've got 4 variables here, always define what each variable is going to be. Okay? Now, what's changing all the time? Well, what's changing is the number of years since 2005. If we were talking about 2006, that's just 1 year. If we're talking about 2007, that would be a 2, because that's 2 years. So X is going to be your independent variable, and it is changing based on the number of years since 2005. That's what it says up here, since 2005. So X is the number of years since 2005. All right? Our Y value, what we're actually solving for here, is basically what the question is asking. The annual amount of money spent at restaurants. Okay? So how much is spent at the restaurants in billions of dollars? And notice that we've kind of used the 360 billion. Rather than writing out all those zeros, use the truncated version of that. It means the shortened version of that. Let A be your initial amount. Well, how much was initially spent when we started this problem or started this experiment? Well, that was 360 billion. So we're using that 360, and just remember in the back of your mind that that's in billions of dollars. All right, B, how is it growing? Okay, well, this is a growth, exponential growth. It's increasing, so that means addition. We take that 100%, 1, and we add in how much it's growing every year, and it's growing 7%. Now, remember, it has to be written as a decimal, so 0.07 is 7%. So when you add those together, you get 1.07. So here's your function. $360 billion is our initial amount, times our growth factor, 1.07, to the x power, x representing the number of years since 2005. All right, so we have our equation, our function. So let's go ahead and apply this function to this problem. We want to predict the annual spending in 2015. So how many years is that since 2005? 2015 is 10 years since 2005. Okay, 2015 minus 2005, 10 years. So we're going to use 10 as our x. So in place of x, we just put 10, because remember, x represents the number of years since 2005. And just solve that. You can plug that in your calculator if you want to, and you're going to get approximately $708 billion. So come this time next year, around next year, maybe this is done at the end of 2015 to kind of add it all together, $708 billion will be spent at restaurants in the United States. So by using that exponential growth, we can determine, using that function, we can determine future trends in based on what we see right now. So let's look at an example, another example. What is an expression that represents the equivalent monthly increase of spending? So I'm just going to bring this up and just kind of show this to you. How many months are there in a year? Okay, well, there's 12 months in a year. All right. Now, what we're looking at here, and this gets a little confusing, but you will need to find an expression in the form r to the m power. R is approximately the monthly growth factor. Okay, we've been doing yearly growth factor. This is approximately monthly. And m is the number of months. Okay. Now, you know that 1.07x represents the yearly increase. Okay, we talked about that. That's our yearly increase there. We want to change it to months. Okay, because what if we wanted to test this in, say, March of 2015 rather than the end of 2015? So what you're going to do is x represents your number of years. That would be the same thing as 12 over 12. 12 divided by 12 is 1 year. Okay, so that's how they simplified that. All right. And then you've got your power raised to a power. Okay, so what they did is they separated that. 1/12 times 12 to the x power. Remember, when you have power to a power, you would multiply those together, so you would wind up with this. They just went backwards. They divided, basically. They split it apart. 1/12 times 12x. Okay, so exponent raised to an exponent, power to a power. They just split that. Then what they did from there, because see, you can't actually take 1.07 to the 12x power, because you don't know what x is. The reason they split this into two pieces is because you can actually take 1.07 to the 1/12th power. So you could type that in your calculator, and this is what you're going to get. You're going to get approximately 1.0057 to the 12x power. Okay, because remember, I can't do anything, I can't break that apart like I did this up here. I could actually break this apart and make that 12 and then the outside be x and break this down even further, but then that would be taking us back to where we were originally. So what we're looking at is 12x equals m. That's the number of months. Okay, so if we're talking about 36 months, which you could translate that to years, but the number m represents the number of months, so 12x is going to represent our m, and so that would be just change 12x to m. And so this expression, what it does is it tells you it represents the equivalent monthly increase of spending at a restaurant. So we could analyze based on months rather than based on years is what this would do. Okay? All right, so what I want you to do, now it's your turn. This is the only example that you're going to get to, and you're definitely going to have to pause the video and solve this. But read this word problem, go through, solve it, write the expression, write out the exponential form, how it's originally written, and then start filling in all the pieces. Make sure you identify what the y, a, b, and x stand for. And then try to write the expression to represent the equivalent monthly cell phone subscription like we did with the last one. Now, I'm going to show you some answer choices for you to pick from. My hope is that you'll at least get the first part, how many subscribers you're going to have. The second part might be a little bit of struggle, and that's okay. So pause the video, please. All right, hopefully you worked on that, and this is your answer. And we'll talk about that when you